On April 20th of last year, a spacecraft the size of a grand piano passed within 600 miles of a rock drifting through the asteroid belt between Mars and Jupiter. The rock was half a mile wide and shaped like a peanut. Nobody had ever seen it up close before. Nobody had ever measured its rotation precisely, or analyzed its surface chemistry, or known anything about it except that it existed and that it was elongated enough to be interesting from a distance. The spacecraft was called Lucy, and the images it sent back from that encounter have been in the hands of scientists for more than a year. Last week, those scientists published what they found in the journal Science, and the results changed something that planetary scientists thought they understood about how asteroid collisions work and what those collisions leave behind. By the end of this video, you will understand what the spacecraft saw, why a wobbling rock in the asteroid belt rewrites part of the textbook on collisions, and what it means for every future mission that goes near an object like this one. Let's get into it. The asteroid is named Donaldjohanson, and the name is worth pausing on for a moment, not because it matters to the physics, but because it tells you something about the spirit of this entire mission. Donaldjohanson is a paleontologist, not an astronomer. He's the scientist who in 1974 in Ethiopia excavated the fossilized skeleton of one of the oldest known human ancestors ever found. That skeleton was given the nickname Lucy. It became one of the most famous fossils in history, and the spacecraft sent to study the most ancient objects in our solar system was named after that skeleton, which means the asteroid visited on the way out was named after the man who found her. There is something in that chain of names that captures what this mission is actually about. Lucy the spacecraft is hunting for fossils. Not biological ones, not bones, but rocks so old and so unchanged that they preserve a direct record of what the early solar system looked like before the planets as we know them were finished forming. Donaldjohanson was not the main target. It was a waypoint, a test run. The real destinations are the Jupiter Trojan asteroids, a population of primitive objects that have been locked in their orbits for billions of years and may be among the most pristine material left over from the solar system's formation. The first of those encounters happens in August of 2027. Donaldjohanson was the warm-up act. And it turned out to be a warm-up act that nobody expected. To understand why the findings from this flyby matter, you have to understand what scientists thought Donaldjohanson was before Lucy got there. Astronomers had been watching the asteroid from Earth for years, tracking the way its brightness changed as it rotated. When an elongated object turns in space, it alternately shows you its wide side and its narrow side, and the brightness shifts in a predictable pattern. From those brightness changes, scientists calculated that Donaldjohanson was completing one rotation every 10.5 Earth days. That is a slow spin by asteroid standards, but it is a clean one, a simple back and forth in brightness that suggested a straightforward single-axis rotation. You point one pole up, you point the other pole down, you spin at 10.5 days, and the brightness follows a regular rhythm. That was the model. The first thing Lucy's close-up images did was confirm the shape the brightness data had hinted at. Donaldjohanson is a contact binary, two separate lobes, each heavily cratered, connected by a narrower neck. The scientists kept reaching for the same word to describe it: peanut. Not a perfect sphere, not a potato, not the kind of irregular lump most asteroids turn out to be, but something that looks distinctly like two objects that came together and stayed together. The two lobes are the dominant visual feature in every image Lucy returned. They are obvious the moment you see them, and their existence immediately raises a specific question. How does a contact binary form? The answer to that question is exactly where the collision story starts. A contact binary is not a coincidence. Two objects do not drift through the solar system and gently stop when they touch. What happens is that a larger body breaks apart in a collision, and the fragments that result begin to interact gravitationally. Some fragments escape entirely, some get captured by the largest remaining piece, and under the right conditions, two similarly sized pieces settle into orbits so close together that they eventually merge, touching at a single point and staying there. The smooth neck region between Donaldjohanson's two lobes is the physical record of that merger. It is the seam. It is where two things that used to be separate became one thing that is loosely held. And the material in the neck, different in texture and topography from the rougher, more heavily cratered lobes on either side, suggests it formed differently, at a different time, under different conditions. The lobes carry the older record, the neck is younger. And the fact that the neck is smooth while the rest of the surface is not, is a signal that something happened there that reset the surface. The density of craters across the two lobes was also telling. Lucy's imaging was sharp enough to map craters down to fairly small sizes, and what scientists found was a consistent crater density that matches the known age of the Erigone family, the collisional family Donaldjohanson belongs to, which formed roughly 155 million years ago. But below a certain size threshold, around 400 meters, the small craters are missing. There are far fewer of them than you would expect if the surface had been quietly accumulating impacts since the family formed. Something wiped them out or prevented them from surviving. The most likely explanation is seismic shaking. When a large impactor hits an asteroid, the shock wave travels through the body and shakes the surface. Loose material slumps into low spots. Small craters, which are shallow relative to their width, get filled in or erased by the movement of surface material during the shaking. The absence of small craters on Donaldjohanson is itself a record of at least one significant impact event after the initial formation, an impact large enough to rattle the entire body and resurface parts of it from the inside out. The asteroid is not just the product of one violent event 155 million years ago. It has been modified by subsequent events, and the surface topography is a layered archive of that entire history. Now here is where the second surprise comes in, and this is the one that changes the textbook. When Lucy's data came back and scientists analyzed the rotation in detail, something was wrong with the 10.5-day number. Or rather, it was not wrong exactly, it was incomplete. Donaldjohanson is rotating every 10.5 days in one direction, end over end, just as the ground-based observation suggested. But it is also wobbling on a second axis, completing that wobble every 26.5 days. Not spinning on two axes at the same time in a stable way, but tumbling, the way a badly thrown football tumbles end over end while also drifting sideways. The technical name for this state is non-principal axis rotation, and it is important because it is not how most asteroids move. Most asteroids, left alone long enough, settle into a clean single-axis spin. The physics pushes them there. Internal friction, even in a loose rubble pile, gradually converts the energy of a tumble into heat, and as that energy drains away, the tumble decays into something simpler and steadier. An asteroid that is tumbling instead of spinning cleanly has not had time to damp out, or something disturbed it recently, or both. Donaldjohanson is tumbling, and the researchers built a model to explain why. The answer they found connects to something most people have never heard of, a force so subtle that it sounds almost fictional, called the Yorp effect. Yorp stands for Yarkovsky, O'Keefe, Radzievsky, and Paddock, four scientists whose work collectively describe the way sunlight can change the rotation of a small body over long timescales. Here is how it works. When sunlight hits an asteroid, most of it is absorbed and re-radiated as heat, but the re-radiation is not perfectly uniform across the surface. An irregular shape with slopes and ridges and rough terrain re-radiates heat in slightly different directions from different parts of the surface, and all of those tiny, unequal pushes of re-radiated heat accumulated over millions of years add up to a net torque on the object, a persistent, tiny twist that either speeds the asteroid up or slows it down, depending on the shape. For Donaldjohanson, the model says Yorp has been slowing it down. Long ago, after the collision that created it 155 million years ago, the asteroid was spinning much faster. Over millions of years, YORP gradually bled away the rotational energy, and as the spin rate slowed, it passed through a specific threshold where the two-lobe geometry, the peanut shape, set up a rotational resonance. A resonance is when two periodic motions interact and lock together, reinforcing each other. When Donaldjohanson's spin rate dropped to just the right value, the geometry of the shape started pumping energy into the second axis of rotation instead of damping it out. The result is what Lucy measured. A tumble born not from a recent impact or a sudden kick, but from the slow, grinding action of sunlight on an irregular shape over tens of millions of years. That is the rewrite. The textbook assumption was that if you see a tumbling asteroid, something hit it. A recent collision knocked it out of its steady spin. The working model for most observed tumblers in the asteroid belt was some kind of external disturbance within the past few 100,000 years. Donaldjohanson says something different. It says you can build a tumble from the inside out, through nothing more than the shape of the body and the patient, invisible pressure of sunlight, without any collision at all. This matters more than it might initially seem. Astronomers catalog asteroid rotation states to understand the history of the asteroid belt, to work out which objects have been disturbed recently by impacts, and to identify which ones are spinning fast enough to be at risk of fragmenting. If a subset of those catalogs has been misclassified because scientists assume tumbling always means a recent hit, then some of the age estimates and collision histories built from that data are built on a wrong assumption. The number of asteroids currently observed in tumbling states is small, roughly a few dozen well-documented cases, but the asteroid belt contains hundreds of thousands of objects larger than a kilometer, and the ones we can measure rotation states for are only a fraction of the total. If Donaldjohanson's mechanism is not unique, if other peanut-shaped or bilobe bodies are sitting in similar resonance states for the same reason, then the true population of sunlight-driven tumblers could be considerably larger than anyone has estimated. And if you are planning to land on one of those objects, or to deflect it, or to mine it, knowing whether it is tumbling because of a recent hit or because of its own geometry is the difference between one kind of engineering problem and a completely different one. The discovery is academic on the surface. The implications run into every future mission that has to dock with an object like this. And then there is the third discovery, and this one reaches the farthest back in time of anything Lucy found at Donaldjohanson. The spacecraft carries an infrared spectrometer, an instrument that reads the chemical signature of a surface by analyzing how it absorbs different wavelengths of light. When that instrument scanned Donaldjohanson's surface, it found iron-rich clay minerals. Clay is not an exotic mineral. You find clay on Earth constantly, but clay has one specific essential requirement. It cannot form without liquid water. Clay minerals are what you get when water reacts with silicate rock over time, slowly altering the chemical structure of the minerals at the surface. There is no other known pathway to form them. If you find clay on an asteroid, you are finding the chemical record of a time when that asteroid, or the larger body it came from, had liquid water somewhere inside it. Donaldjohanson does not have liquid water now. It is a rock in space, and space is cold and dry and without the pressure needed to keep water liquid at the surface. But 155 million years ago, before the collision that created it, Donaldjohanson was a piece of something much bigger. The parent body for the Aragon asteroid family, the group Donaldjohanson belongs to, was an asteroid roughly 50 miles across that was struck by an object about 12 miles wide and shattered into nearly 1,800 identified fragments that we can still trace today. That parent body, before it was destroyed, was large enough to retain heat from its own formation and from the decay of radioactive elements inside it. In the early history of the solar system, that heat could melt ice. Water, once liquid, reacts with rock, and the clay minerals now sitting on the surface of Donaldjohanson are what survived that reaction, preserved for over 100 million years in the fragments of a body that no longer exists. The clay signature connects Donaldjohanson directly to a category of carbon-rich, water-bearing asteroids that scientists have been studying through meteorites for decades. The match is close enough that the team compared the spectra to specific meteorites already in collections on Earth and found chemical signatures that are nearly identical, which means that some of the meteorites already sitting in laboratories, already analyzed, already catalogued, came from the same kind of body as Donaldjohanson and carry the same preserved record of ancient liquid water from the early solar system. We have had physical samples of bodies like this in our hands for years. Lucy's flyby is the first time we have seen what one looks like up close. There is a direct line from what Lucy found at Donaldjohanson to a question that has come up on this channel before, the question of what actually happens when you try to interact with one of these objects, whether for science or for planetary defense. In 2022, NASA's DART mission deliberately hit an asteroid moonlet called Dimorphos and changed its orbit. It worked. But the biggest surprise from DART was how much the outcome depended on the internal structure of the target. Dimorphos was a rubble pile, a loose collection of material held together by its own weak gravity, and when the impactor hit it, the surface splashed outward in a massive debris plume that pushed the asteroid harder than the impact alone would have. The deflection was larger than expected precisely because the body was soft and loosely packed. Now here is what Donaldjohanson adds to that picture. Donaldjohanson is also a rubble pile, a contact binary with a weak neck, a vulnerable seam where two loosely connected pieces meet. It is tumbling in a state that nobody would have predicted from ground observations alone. It carries clay minerals that tell you the material is chemically altered and hydrated, potentially different in density and cohesion from a simpler stony body. Every one of those properties matters if you ever need to interact with an object like this. Knowing whether something is tumbling because of a recent hit or because of its own geometry is the difference between one kind of engineering problem and a completely different one. DART proved the principle works. Lucy is filling in everything the principle requires to actually be applied. That gap is what the next decade of asteroid science is trying to close. Here is the part that the scientists are being careful not to overstate, and it is worth being precise about. The water on Donaldjohanson's parent body was not a habitable environment in any sense that maps to life as we know it. It was heat-driven chemistry, water moving through rock under pressure, the way hydrothermal systems work inside a body too small to have a real geology, but large enough to stay warm for a few million years. The clay minerals are not evidence of a planet with rivers and oceans. They are evidence of a warm, wet, chemically active interior that existed briefly in the early solar system, before the parent body cooled and was eventually destroyed. The distinction matters because the same chemistry, on a much larger scale, is part of how Earth became the kind of planet it is. Water-bearing asteroids crashing into the early Earth over billions of years are one of the leading candidates for the source of Earth's water and the organic molecules that preceded life. Donaldjohanson is a fragment of exactly that kind of asteroid, small enough to study up close, old enough to carry the record, and now documented in detail for the first time. What Lucy does not yet have is a sample. Every conclusion from this flyby is drawn from remote sensing, from images and spectral data taken at high speed from 600 miles away. To actually hold the material in your hands, to run the full suite of chemical analyses that would confirm or complicate the picture, you would need to land and collect or send a sample return mission to an object from the same family. That has not happened yet for this class of asteroid. The findings published in Science last week are the best remote portrait ever taken of this type of body, and they already push the science significantly further than it was. But they are also the opening paragraph of a much longer question, not the final answer. Lucy itself has a long journey ahead. The spacecraft spent Donaldjohanson as a dress rehearsal, testing its instruments and its terminal tracking system, which autonomously points the cameras at the target during a high-speed flyby without human input, because the light travel delay to Earth makes real-time control impossible. That system worked, the cameras worked, the spectrometer worked, and what they produce from a single close pass at an unremarkable rock in the asteroid belt has already rewritten two things scientists thought they knew. The tumble that researchers assumed meant a recent impact turned out to mean something else entirely. The shape that looked from Earth like a simple elongated rock turned out to be a contact binary with a neck that preserves the merger of two separate pieces. The surface chemistry turned out to carry water signatures from a world that no longer exists. The next encounter is in August of 2027, when Lucy reaches Eurybates, the first of the Jupiter Trojan asteroids. Trojans are a fundamentally different population from main belt asteroids. They are thought to have formed in the outer solar system, in the same cold, primitive region that produced the objects beyond Neptune, and to have been captured into their current orbits during a major rearrangement of the outer planets early in solar system history. If Donaldjohanson, a relatively young fragment of a collisional family in the inner belt, already carries this much information about water and collisions and the slow action of sunlight, the Trojans, older and more primitive and never incorporated into anything larger, could hold a record that reaches all the way back to the first few million years of the solar system's existence. The researchers working on Lucy said it themselves in the paper. Once we start learning more about the Trojans, our understanding of solar system formation is destined to be challenged. Donaldjohanson was the warm-up, and the warm-up already changed the picture. We will be tracking Lucy's next encounter closely. If you made it to the end of this video, go ahead and hit the like button. It genuinely helps this channel reach the people who want to know what is happening out there, and there is a lot more to cover. Subscribe if you are not already, drop a comment with the thing from this video that surprised you most, and we will see you in the next one.